It's like 3 minutes past. I guess we can start. So just a note that the talk might be recorded. So if you are uncomfortable with it, you can let us know. You could just shut off your video and your audio, and there will be no trace of you. So let's start off by just an interesting thing I learned on sort of preparing for this. How pythons actually kill. From sort of growing up, I sort of always known that they're sort of, I thought they were strangling their victims. They actually aren't. So what they do is they have these backward pointing teeth. And what they do is sort of they bite you, and they use that to sort of grab the prey. So they grab you, they attach themselves to you. And then, of course, the victim is sort of constricted. They sort of wind themselves around you. Yeah, just like in any cartoon. But what actually happens when they sort of wind and they start sort of pushing you is that the blood flow is severely impeded. And this actually leads to cardiac arrest. So your actually heart stops because of the blood flow stops. Anyway, now for something a bit smaller, the topic of today, Micropython and how can you sort of use it to do rapid IoT prototyping. You actually need to speak up if you need to if you want to stop me and ask a question, that's perfectly fine. But since I only have one screen working, I can't actually sort of see you. So raising your hand won't actually do anything. Just speak up or try to wave at Andreas Bade, and he can, or write it in the chat, and he can sort of deal with it. Okay. This is me. My name is Buer. I work in Knowit ObjectNet. This talk is sort of part of their sort of competency building program. And earlier this year, we partnered up with Bitraf. And this talk is sort of shared with Bitraf in light of that partnership. Other stuff I've done before coming to ObjectNet, I spent 3 years building an operating system called IncludeOS, and I did the open source stuff, other open source stuff before that. Okay, so what are we going to talk about today? So first, we'll talk a bit about microcontrollers, what they are, how are they different from regular computers. I'll give a 15-second introduction to Python, and then we get started with Micropython. Try to give you an overview on how it works, why I think it's a good idea, and then we'll try to build stuff. So first, microcontrollers. So for those who aren't familiar with them, they're very, very simple computers. They don't have a sort of traditional operating system. They are typically sort of single-purpose devices, so they run only one thing. So they don't compare that to your Raspberry Pi or to your laptop, where you can sort of run multiple applications. Microcontrollers typically aren't used for running multiple things. They're typically cheap. The microcontrollers we're talking about today are in the $2 to $8 range. You can get more expensive microcontrollers as well, but typically there are a lot of the motivations for using them in a task is because of price. They have these pins that you can see there. We refer to them as general purpose I/O pins. They allow you to sort of connect other stuff to them, so you can sort of use them to sense the world around you and to influence the world around you. And the cool ones, they have Wi-Fi or other internet connectivity, and sort of that turns the microcontroller into an IoT device. So these two which are the ones, I'll concentrate on today. On the left there, you'll see the ESP8266. It's super, super cheap. I think like $2 or something. There's one sort of limitation with it. It only has one analog pin. So if you want to sort of read the signal that's not a 0 or a 1, you might you can only do that for one signal. It's interesting sort of how it got popular, because it started its life mostly as a Wi-Fi chip for the Arduino. So people would buy these modules that would give the Arduino Wi-Fi capabilities. And it contains like, I think, I can't remember how much, but like 64 kilobytes of memory or something like that. And it has a CPU that runs at 80 megahertz or something. So people started wondering, why are we actually using the Arduino with its sort of puny 16 megahertz microcontroller when we could use this thing directly instead of just having this just do Wi-Fi, because it's more capable than Arduino when it comes to sort of doing calculations and stuff, and that's why sort of people started using it in some situations instead of the Arduino. That's on the right. You see its bigger brother, the ESP32. It's still a cheap microcontroller. You typically pay maybe $4 or $5 for them. Have quite a few pins on them, so you can connect tons of stuff. The GPU pins are a mess. There are hundreds of different versions of these modules, and each of them have a slightly different pin layout. So I spent a lot of time Googling. Both of these are Chinese products. They're made by this company called Espressif. They are not really that good at sort of this whole open source thing, but they are learning, and they're becoming more and more proficient at actually building a community for each year. Yeah. So we'll talk a little bit about sort of the typical stuff that we attach. I mean, typically we use these devices to sense the environment, temperature, pressure, humidity, things like that. Measure distances is something I've done quite a bit, either with sort of ultrasonic sound or with IR sensors. You have various motion detectors, accelerometers, gyroscopes, and then for sort of actuators, so actuators are things that actually do something, and like sensors which just sense something. So I would say perhaps the more typical ones are relays. So if you want to sort of create your own smart lamp, you want a relay to sort of turn it on and off. LEDs and displays are also sort of typical ways to sort of signal something back to the world. Yeah, and then servo stepper motors if you want to sort of move something. So back to the sort of topic of the day. What's my motivation for doing this with what problems I had with Arduino? One is that it's C and C++, and C and C++ is hard and dangerous. I'm not really a good C or C++ programmer, so I struggle a lot with sort of casting void pointers and sort of trying to do that, and I make a lot of mistakes. I wanted to speed up the time it took me to actually create something that's useful. Earlier this year, I spent probably a whole day just parsing JSON in C++ on a microcontroller, so I couldn't use the sophisticated libraries. You have to use these very primitive libraries. It feels a bit like you're parsing JSON by smashing two rocks together, which is not. Also, Python's easy syntax means this can be used for everybody. I think I get a lot of personal pleasure out of blinking LEDs and sort of creating these little devices that actually do something. It sparks joy in my life, and I want to sort of share that and sort of give more people the opportunity to sort of step away from sort of this cloud native development bullshit and actually just create something very simple that you can fully understand how it works without writing any YAML. So there are a few limitations with MicroPython. You can't have real-time code. So basically that means that if you are relying on things to be sort of timing to be sort of an exact factor in the program you're writing, so you want to receive a message or a pin goes high and you want to respond within, let's say, yeah, I don't know, 30 microseconds or something. You can't do that in MicroPython because it's a garbage collected language. It might be garbage collecting. It actually there's an operating system built into it, FreeRTOS. So FreeRTOS might do some housekeeping. And if that happens at the wrong time, then you'll miss your deadline. Yeah. On-device security is very weak. There is no encryption. If you take any of my devices and you plug them into a computer, it'll happily give away all its source code, all its secrets, and everything. There's nothing sort of protecting it. I haven't really found any way to do it, and I don't really have a need for doing that. All my devices are typically, yeah, they're not confidential. So power consumption is higher. MicroPython executes a bit slower than C and C++. So if you want to do things like wake up, do something, go back to sleep again, you can do that, but you'll actually have to spend a few more milliseconds in the while you're awake, while the microcontroller is awake, and that might sort of reduce the lifespan of your battery-powered sensor. Drivers aren't as plentiful and as on Arduino. I haven't really found that to be a impeding factor in any way. I think I have one, like a LED matrix. Yeah, I can take this thing here. I don't know if my camera works, but perhaps you can see it. It's the sort of 16 by 24 LED matrix. This thing, I can't get it to work with MicroPython. Other than that, I've gotten everything to work. Okay, so Python. Like why Python? Or what is it? Yeah, interpreted language from the early 90s. I think it started out as a general purpose language. And today it's extremely popular among the machine learning crowd, also a lot of sort of system stuff. So Google has a huge Python community inside of it where they do automation and things with it. Its primary focus is on the readability of code. So you're told to avoid the clever stuff. So that's when you sort of try to do these neat constructs that do a lot of stuff in just one line of code. That's not really proper Python. You should avoid doing that if you can. And what's called the REPL, which is the interactive prompt of Python, allows you to sort of quickly test stuff and sort of see that this is valid Python and it does what you think it does. Yeah, let me show you. So let's see if we can. Well, I think I'll just. Yes. So typically, sort of when I write Python, I typically, yeah, this is. You can probably see this. Let's make it a bit bigger. So this is just a sort of silly example with a sort of function that sort of calculates the Fibonacci sequence in the naive way. It's probably slow and horrible. And typically, sort of when I would write code, I would just start up Python and I would import the file that I'm working on. So this is called fib.py, so I import it. It runs some code. That code, which is outside all the function definitions, is just run. And now I can sort of play around with it. So it has now created a namespace called fib, so I can do fib, and I can just tab, and I see I have a bar, a foo, and a recursive Fibonacci.
So these are foo and bar, which you see are just variables. So I can inspect foo, it's 15, and I can call thing and ask it to calculate the 9th Fibonacci number, and that's 34. And this sort of without sort of printf statements or debuggers or anything. I just sort of mostly write libraries which I then sort of import into the Python interactive shell, the REPL, and then I just sort of play around with it there and make sure that it works. And then I sort of write my initializing code at the end. Yeah. So let's get back to where we are. Oh, yeah. And now it's time to start talking about Micropython. So Micropython basically is a re-implementation of Python 3.x. I think it's around 3.5, not entirely. It's not exactly 3.5 because there are some stuff that's missing from Micropython. Some things which are very sort of convenient is really hard to do on a microcontroller because it requires a lot of memory. A Micropython runs, I think, on the smallest things it runs on is like the BBC, the BBC microbit, which I think has like 16 kilobytes of memory or something, which is tiny. So you can't do everything. Yeah, supports 95% of Python. Approximately between 10 and 100 times slower than C or C++. That sounds like a lot, but like that ESP32, which I talked about earlier, it has a clock speed of 240 megahertz. So it's actually, I mean, it's not super fast, nothing like your computer or anything, but it's fast enough so that if a code runs 100 times slower, that's might often be fast enough. And so far I've never been needed extra. I haven't had to scrap anything because it's too slow. Yeah, and it runs on a bunch of microcontrollers. Yeah, microbit, as I mentioned, the ESPs, and there's also a PyBoard family, which is a family of microcontrollers which are specifically created to run MicroPython. They're a bit pricey. They're made in Germany, which is like the only thing I have which is electronics and made in Germany, but it's really nice. Yeah. There is also probably lots of other stuff it runs on. It also runs on Unix as well, so you can actually run it on your regular computer if you want to test stuff. Installation is pretty straightforward. You download the version of MicroPython that you need. Yeah, they have different versions for different microcontrollers. You plug in the microcontroller that you want to install on. Microcontrollers, they typically have either built-in or there's a serial adapter on it, so it presents like a serial port. So on Windows, that might be COM9. On Mac OS, it's dev.cu.something. On Linux, I think it's like dev.ttu USB 0 or something like that. So now you get to this serial port. You install this tool called ESP tool. And then you use that ESP tool to sort of flash those images onto the device. So that's one of the commands. Yeah. I'll just leave it there for reference. I'm not going to go through it. Yeah. Once you've done that, that's the sort of only time-consuming tasks that you have. It writes out the image and resets and boots up Python, and from that moment on, you can use it. Yeah. You can use a terminal prompt, terminal program to get the REPL prompt, or there are also some other tools that you can use. We'll get to that in a moment, demo. Yeah, and since this is a dynamic language, so what you actually download to the microcontrollers microcontroller is the actual source code itself. The source code itself is compiled on the microcontroller, so that allows you to actually interactively test stuff. So you can, the same way I did play around with sort of the Fibonacci sequence in the prompt, you can do that on the microcontroller as well. There's a file system created in flash memory on the device. And whenever it boots up, if it finds a file which is called main.py, that file is executed. So you can sort of place random content there. You can place JSON configurations, you can play Python libraries, but the only sort of magical file is main.py. Compare this to Arduino or any other sort of traditional microcontrollers where you have to sort of compile and flash the program onto the device every time it changes, and that compile and flash sequence might take 3-4 minutes. It's quite convenient. Yeah, so there's this other tool called PyBoard, which just allows you to just grab a Python file and just sort of shuffle it to the device and run it right away. Yeah, so let me see if I can show you this. Now things get a bit more complicated because I need to show you my camera, other camera, which I think you can see there. So let's do a simpler thing. I'll just need to start R shell, which gets me the REPL prompt. Now I'm sort of, so the device you can see on screen is at my desk here, and that's what I'm now running sort of Python code on that device. You can do your typical hello world like this, and that works. So that goes over the serial line, yeah, and gets back that same way. That's not really that exciting. What we can do is there's a library called machine, and it has a class called pin. So we'll import that, and we can import this sleep function from the time library, and now we can define a variable or an object. We'll call that LED, which is connected to GPIO pin 2. So that's, yeah, now I have and I can do things like turn it on. And you see the blue light there, that turns on, and I can turn it off again. So that sort of shows you a bit of sort of how sort of convenient it is to sort of interactively play with the hardware that's attached to your microcontroller. Let's disconnect from this a moment, and I showed you the command line to PyBoard, which is just this simple utility which just sort of dumps that Python file onto the device. So this program is called simpleblink.py, the one that you see in the editor window. And I can just run it like this, and I would sort of run it on the device. So it runs instantaneously. There are probably the editor integrations that would allow me to just push a button in the editor and just run it there, but I don't mind it doing it on the command line. That's pretty cool, right? Yes, I just assumed that you're nodding. Okay, so tools that you'll need in order to do this. Pybar.py, that was the one that was running foo.py on the device. It can also be used to copy things to the device. There's something called rshell, which you saw me use earlier, which is just a simple way to get access to the REPL prompt. Or you can just use screen or serial terminal or something for direct access to REPL. I think I have one of those here as well. Serial, I think. Yeah, this thing. Which is just sort of, this is a serial terminal program. I just sort of so that's not, so you can use anything. So that sort of also showcases the rather lax security. Now let's blink that LED again, but we'll make it a bit more complicated this time. We'll make it blink whenever I move around. So the first thing, sort of when I this is sort of my most frequent Google term, is like ESP32 pinout. I should probably store them locally so I don't have to look it up every time. But that's part of the problem with this ESP32 module is that the GPIO pins might be different from there's also subtle differences between two modules, and also they're marked. So they might have like pin 17 is pin 17, but it might not be GPIO 17. So you, look at the physical pinout. There's Wi-Fi antenna on this. There's the reset button, and there's a micro USB connector as well. So in order to sort of blink the LED whenever I move around, I could do things with sort of just pulling it and doing it in a while loop, but I'm much rather do it in an interrupt. So interrupts, for those of you who haven't done sort of low-level programming, is the system gives you an ability to sort of hook code onto specific events. And for microcontrollers, those are typically either timers or when a GPIO pin changes state. So when it goes from high to low or low to high, you can sort of run your code. So you can run code on rising flank, so that when it goes from 0 to 3.3 volts, or from falling flank, we come back again to 0 again, or on any change. And the way that it sort of works is you have your main program that sort of executes, and then the event happens, and Micropython runs your interrupt handler, which then is the thing that runs, and then you return to executing your main program again. Yes. So I think I'll just go through sort of the code that you see on screen. This is quite simple, really. So we can make it run afterwards. So the first thing is that I have I create an object called Buer, which is a passive infrared sensor, which is connected to pin 23. I tell it that it's a input pin, so I'm not going to use that pin for output. I'm going to use input. Then you have the LED, which you saw earlier, and then I create this interrupt handler, which takes a parameter, which is the pin that triggered it. I don't use that here, but you could imagine monitoring multiple pins with one interrupt handler. When we've done it, pins movement detected, it turns the LED on, sleeps for a second, and then turns the LED off. That's the whole function, really. There's a print statement there, which will just run whenever this is run. And then I set up the interrupt handler. So, and you can see it's a function on the Buer object.
So it's a function on the pin class, which I then invoke, and I give it, say that I want to have this on a rising flank, and then I give it the handler, which is a reference to the function you see above. Notice the lack of parentheses. So in Python, when you just write the name of a function, that is just a reference to a function. Whenever you add the parentheses, you invoke the function itself. And then there's just a stupid while loop just to sort of just keep on running, so that I'm not sure if that will be needed on an actual, when I run, if I copy it, call it main.py, but it's needed whenever I run it interactively. So let's see if we can make this work. So this is the polygon peer. Yeah, here you have the same code, which I talked about earlier. And run it. And it detected movement. That was me probably moving a bit. I think it's a pretty stupid sensor, and I think like if I move my head now, yeah, it detected the movement again. I think like whenever it detects movement, it can't detect movement for 5 or 8 seconds or something. So it's not, yeah. Okay, let's get back to the slides. Keep on. Yeah, questions so far? Just should check that you're all here. Yes, that's good. Okay, so no questions. That's great. Okay, let's connect more stuff. Let's use I2C. So I2C, it's a bus. So bus is a thing where you can connect multiple devices. You connect many devices, and you just require 2 pins. So for the ESP32, pins is not really an issue because you have tons of them. But for maybe the ESP8266 and smaller devices, you might be constrained with the number of pins that you have. So connecting multiple devices to the same pin is valuable. On the I2C bus, there's just 2 pins. You have one called SDA, which is used for data, and then SCL, which is used for clock. Yes, so now we're going to try to build something again. Let me see. Yes, we're going to use the ESP32 again. I'm going to use the BMP280 sensor, which is an I2C sensor, which gives me temperature and pressure. And I'm going to use an OLED display, which is a tiny little display, 0.96 inches, I think, so 2.3 centimeters across diagonally, which uses the same I2C bus, or I2C bus. So this is what sort of the breadboard looks like on this. And as you can see, sort of, I'm using a different ESP32 module. This is a completely different one. It's a super fancy one. It has an SD card and a battery connector. It also has external memory soldered onto it. I think that's one of the pins, one of the chips you see there is a memory chip. So you can see that they're connected to the, that's not, yeah, the gray wire there is connected to the ground rail, the breadboard. I also give it power, which I get from the microcontroller itself. And I think there's some sort of convention that you're supposed to use GPIO 21 and 22 for SDA and SCL on the ESP32. Might be that there's some hardware in there which does the actual I2C stuff. I don't know. That's the BMP280.
And that's the little OLED display, which is tiny. Yes, yeah, regular. Okay, so let's. I'm gonna now see if I can disconnect this thing, and I'll connect the other microcontroller, which has this. Huh. What? Okay. Seems to be some weirdness with QuickTime. Yeah, there we are. Okay, so let me see if I can put the wires a bit out of the way. No, they won't do that. Yeah, that works. Great. And let's see if we can interactively explore the I2C bus. We'll get the REPL prompt. And from the machine library, I import the I2C class. And I create an instance. And I can't remember which one was the SDA was 21. Okay. Oh, yeah, it needs a pin, not just the number of the pin. So I can declare it straight away in here. Pin out. Yeah. And this one, pin 22. Of course, pin isn't defined from machine import pin. Now let's try this again. It works, or it run, and then we can do scan. And it scans that to C-bus. It says me there are two devices. One has address 60 and the other one has address 118. Now, for those of you who sort of been struggling with I2C on Arduino, when the first time I did this, my sort of head exploded a tiny bit, because that was pretty cool. Because I could do that without sort of all this back and forth and building that code right and running it right on the device. I felt very productive that day. Okay. So let's go back to the presentation again. Yeah, here you see the correct way of doing this, where I actually import the pin class right away. And I print, yeah, here I use print because whenever you call a function in Python and you don't do anything with it, if the return value gets printed on the screen, so it's an implicit print statement on anything that's just a naked function call. Okay, so now we're going to sort of go through the code, which now sort of connects the BMP280 to that OLED display. So first thing here, it's not really super exciting. From the top here, you see I import machine, and I get the right classes into it. And then I import the SSD 1306 library. And the libraries like machine and time, those are shipped with Micropython. SSD 1306 does not ship with Micropython. I have to actually download it and place it on the device. So I just use PyBoard or RShell just to sort of copy it onto the device. Same for the BMP280. You need to place those the libraries, the drivers that you use that don't ship with Micropython. Those needs to be placed there. You need to place them there yourself. And then there are just a bunch of constants where just to do pin definitions. The const function is, I don't think it's in regular Python. You don't need it in regular Python. What it actually does is it behaves a bit like an include statement in C or C++. So whenever you see pin SCL in that code, that gets replaced with the integer 22. I think it only works for integers. You can't use it for strings and things like that. But yeah. Yeah, and then there's some variables. There's a variable that dictates or that indicates if the OLED device is connected or not, because the code is robust enough to handle that the device isn't connected. And then I just use a bunch of global variables for temperature and pressure and humidity, which, yeah, I thought this sensor had, but it didn't. So that's a tiny little bug there. And then I create OLED class. Those are variables where I'll put the objects for the OLED device and the BMP280 and just declare them there. I mean, this is microcontroller code, and it's just a couple of, I think, like 200 lines of code. So yeah, global variables. Thomas might object to sort of my non-beautiful code, but it's, yeah, it works. And then I instantiate the I2C bus at the bottom there. Yeah, and the code continues. When it starts up, it will scan the I2C bus, and we create a list called devices, because remember that scan function returning a list, those were indicated by the square bracket. So if that list has 0 length, then we complain about it. If not, then we start iterating over them. And as you can see here, these are the addresses 60, and I'm pointing at the screen now, which is really useless because you probably can't see that. But these constants, Adder OLED and Adder BMP, those are the addresses that I'm looking for. So I'm looking for those particular devices. And whenever I find them here, I will instantiate the object, the OLED object, and the BMP object. Yes. So and there's a bunch of just code there, which is, I think, just taken from the example files of those drivers. Yeah. No. And then I get to a main loop, which at least a lot of my microcontroller stuff have. They have this main loop, which is just looping, and it just checks if if it has a BMP connected to it, and then it prints the values and it keeps them in these variables. If it has an OLED display connected to it, it will use OLED.text to output temperature : and pressure : on the little OLED display. Yes, if there's no BMP connected, it says it's not available. And then it just sleeps for 5,000 milliseconds, and then it does it all over again. So let's see if we can get this to run. So this is temp1.py. All this code is available on GitHub. You'll get it afterwards. Yeah, so this is more or less the same code here. Okay, so it seems to. So let me get out of this, and this is my command for running it on the device. And the file is called temp1.py. I can bring the, where's the mouse? Hey. Yeah, so it's not ideal that I say temperature because I cut this. Yeah, so I should probably say temp instead. Yeah, so that's like a pretty quick turnaround for a microcontroller bug. Yeah, so it works. Any questions so far? No? Okay, so let's carry on then. Networking. Yes. Okay, so split into another code dump. I mean, I'm not going to explain to you what Wi-Fi, how it works. Sort of, yeah. So in my projects, I have this VLAN connect function, which I typically just sort of copy and paste. It's not very exciting. It's just some template code. I haven't written this. I just copied it from somewhere. What it actually does is that if it's not connected, that's this line here, which means that because you might actually restart Python, and Python will retain, because there's two kinds of restart. One is a hard restart where the device boots up. The other one is that you just press Control D, which is end of file in the REPL, and then Python itself just restarts. But when Python itself restarts, it actually retains the Wi-Fi connection. So in order not to sort of confuse things, if it's not connected, then we initialize it. And this is my SSID, so my network name, and this is the network password. And then I just loop until this returns. Yeah. So this loop will actually never return if it can't find the Wi-Fi. That might not be what you're looking for. And this is the time I can sort of introduce you to another magic file on the file system, which is boot.py, and how boot.py gave me a hard time. So boot.py is what it sounds like. It runs whenever your MCU boots up. However, you're not supposed to do things in it that might, for instance, not return. And that's because some of the tools, like RShell, will actually make the device restart when it connects. And if boot.py never returns, that means it can't connect. So it will just restart the device and then boot.py runs, and it won't present a REPL shell because it's just waiting for that Wi-Fi to show up. Yeah. So tip of advice is to put networking stuff in main.py, or at least make sure that your device gives up in 5 seconds if it can't find the Wi-Fi. Okay. So JSON. Yeah, you all know what JSON is. JSON in Micropython is super simple. Here I have an object, temperature, where I grab two variables, temperature and pressure, and then I create that into a JSON string with ujson.dumps. Dump, I think, is for dump string, which just I pass the object and it spits out a string. So again, that's pretty convenient. I don't have to worry about string lengths or buffer overflows or anything like that. I just sort of do it and it works. Yeah, so JSON is super simple. MQTT which is the last thing, which sort of, again, which is where we go from this being just silly microcontrollers to being proper IoT devices. So MQTT, for those of you who don't know it, it's a simple PubSub protocol where basically you can publish data on like a virtual bus, and others can subscribe to those data, and the publishers just publish and the subscribers just subscribe, and it's sort of, it's not tied strictly together, so it's asynchronous. So you write stuff onto the MQTT thingy, and it's sort of, and then your device is free to go along. So that means that unlike REST interfaces, for instance, which are synchronous, so if you try to sort of push a temperature through a REST call onto a service, if that service is down or you can't, then that will block, and everything gets more complicated. It was developed for oil pipes. It's also an ISO standard, super common in IoT. Payload is typically JSON. There's a library which I think ships with Micropython, which is umqtt.robust, which is a pretty simple library. The difference between the robust and the .simple is that the .robust will reconnect if it loses connectivity. So you probably want to use that. And here you see sort of just create a, there's a bug on the slide. Sorry about that. Yes. We just instantiate an object. We pass it our unique identifier, whatever that might be. I'm not sure if you need, you need some sort of identifier. It might be just a random string. And pass it the server you want to connect to, and then you connect, and then you start publishing. Yes, so this is the last demo. I'm going to use test.mosquito.org, which is just a public MQTT server that's available for for everyone. And unlike my former adventures in Arduino, TLS is not going to be an issue here. It just works. And then I'll do a command, a Unix command to sort of connect to it, and the -t indicates the topic. So you can see, yeah, this is Knowit object at hardware guild Micropython 0. So that's the identifies the device. You can build yourself this hierarchy of devices. Yes, demo. Okay, so let's see if we can get this thing to work. So I'm not going to focus on this thing. This will just look like it has looked earlier. So this is the new code. It's not really very exciting. There are a few constants here which are set, like the topic. There's the VLAN connect, which connects to SSID and password. And somewhere down here, yes, here I do a send MQTT. And up here somewhere there should be a send MQTT, which takes temperature and pressure. It creates the object that you saw earlier, creates a JSON string, and then publishes it. So it looks super simple. So I'm just going to run it and see if it runs. Yeah, it connected to the Wi-Fi. It's actually, there's some numbers there. I have no idea what the pressure is actually, if I don't really know anything about pressure and why it's 96,000. Yeah, somebody might explain that to me afterwards. And then there should be some sort of, should be like this thing. And I should be able to. So you can see now a lot of these things start popping up. They're very identical. Yeah. I think I might have. Oh, I don't know. Yeah, I'm not entirely sure why I keep getting the exact same temperature. I don't think I think it should vary a bit, but it doesn't. But anyway, that's kind of outside the outside the thing. Yeah. Okay. So, summing up my experiences so far. Getting stuff online is super simple. It's amazing for prototyping. I've also found libraries where I could just place the sensor somewhere, and it would actually pull down code from GitHub whenever I did a release on GitHub. So I could actually pull my microcontroller code to GitHub, and whenever I did a release, the device would pull GitHub and then download the new Python code and execute it, which meant that I don't need any over-the-air fleet management system in order to push code out. I could just use GitHub, commit to GitHub, and then create a version, and then all my devices would update, which was pretty amazing. And it's free of fucking YAML, which I think is amazing because my day job is all about writing YAML these days. Summing up, yeah, I've said that. It's amazing. Prototyping quickly using the REPL is super nice. Networking for doing sensors. And you have these R shell and PyBod things, which you should sort of start to use. Set up a proper a workflow where you can iterate quickly. And don't forget that on-device security is non-existing. For those of you, nobody has commented on that my SSID is SSID and my password is password. They typically aren't, but I needed to be able to show you these without giving away secrets. And there is the URL to the talk, to the code that's referenced in this talk. I think perhaps we can sort of change the meetup invitation, or I'll also publish this on Twitter. The username is the same as on GitHub. And that's basically it.
Yeah, there are two questions on the chat. So, how did you push the code from REPL after update? Maybe you did answer that earlier, but I'm not sure.
How did I push the code from REPL after update? Oh, no, that was, so what I did there was, that was when I fixed the little temperature, the string was too long to fit on the screen, right? I think. Yes. Let's go back to that then. Let me share my screen again. Because that is pretty cool actually. So I mean, what I did there was yeah. The code was just run like this. So here is the code, and I just can edit it here, and I can say instead of pressure, I'll just say PR, and then it just gets pushed this way. So the PyBod command, which just takes the device as an option, and then the Python file which I need to run. So just run this Python file on this device, and then it starts running. And if we look at the little microcontroller now, it should say PR instead of pressure. So I don't. Yeah. So it's actually just pushed over the serial port ad hoc, sort of, for each execution. Since the program is pretty small, and this is a pretty fast serial connection, doesn't take any time at all. Any other questions?
Yeah, there are one more. So Micropython has a Git client?
Yeah, I think so, or at least I mean it's just REST APIs, and you can just do. You have in Python you have this request library. So there's a MicroPython version which is called uRequest, micro requests, which has most of the same functionality. So you can just do REST stuff and download content and yeah. I see if I can sort of push create a reference to it. Yeah, it's not a full-on Git client. It just can just download files from what's tagged as a release inside of in a Git repository. Yeah, and as Bjørnar Mikkelsen mentioned that you have WebREPL. So WebREPL is some sort of, you can use this REPL thing to inside your house to get the REPL prompt in your browser, and you don't have to attach through serial port. I just haven't gotten around to actually using it, but it's probably nice. Yeah. Other than that, I don't think there's any more questions.
One question.
Yes.
One more question. Yeah, about speed.
Yes.
Compared with Arduino, I have a Arduino Uno that measure vibrations 100 times per second, and I need to go to 1000.
Yeah. Oh, so there's with regards to performance. So there are certain operations in Python or MicroPython that are super slow. Things like looking up like global variables take quite a bit of time because you have to look up in these global dictionaries. So there's a whole brilliant talk with the guy who wrote MicroPython on optimizing, and I think on this super tiny controller he's actually able to push 20 megahertz onto a GPI pin or something. So 1,000 times per second doesn't sound scary. I think that should be pretty doable.
It's 1,000 analog reads on 3 channels, so it's it shouldn't be that much. And also Arduino is quite slow at I also.
Yeah, and I mean I have 2 families or 3 families of microcontrollers that I use. I've used the Pi boards, which are super fast. They're blazingly fast. So that's like an ARM M7 or something from STM32, and I had no doubt that it would be able to do it. But the ESP32s are quite slow compared to those, but they're still pretty fast. Yeah, you just have to try.
Yeah, and of course I'm running on 8-bit today, so it should be faster.
Yeah, I think so.
Yeah, thank you very much. Very good presentation.
Oh, thank you. There's a question if I have any experience with PyCom GPy and BOP. I never heard of it, so no. Experience with ASN1 libraries with MicroPython. I don't know what ASN1 is. It sounds familiar, but I'm absolutely sure that I don't know what it is. Is the code compiled before execution on the device? Yes, it's compiled before execution. You can, however, if you want to, you can compile it into MicroPython itself. It will then be available on the device as bytecode, which then speeds up execution. No, it doesn't speed up execution. You skip the compiler step and you save some memory because you don't have to have this textual representation of the source code. And you can also go all the way and have inline assembly and sort of do all that crazy stuff if you sort of want to. But then again, perhaps you should just spend $10 more and get a faster microcontroller. I don't know. Okay, excellent. If there are any more questions, I'll leave you guys for now. It was great presenting to you. I forgot how. It's a bit of a shame that I should have had one more screen so I could actually see you guys whenever I talk, because talking to a wall for an hour is exhausting. Yeah, thank you for your great feedback. I think on Bitraf we should have there's the programming Slack as well as the yeah, that's probably the right maybe the electronics one. I don't know. Great guys, see you guys around.